Welcome to WikiPodcast. What if everything you thought you knew about gravity was, well, fundamentally misunderstood?
Yeah, not just a little adjustment to the old ideas.
Exactly, but a radical reimagining.
Hmm.
The idea that gravity isn't some force pulling us down, but maybe the very fabric of space and time twisting and turning around us.
That's the core of it. It's a beautiful geometric picture.
So today we're doing a deep dive into Albert Einstein's General Relativity. We'll try to unpack how this really mind-bending concept works and what it actually means for, everything from apples falling to the biggest structures in the cosmos. Okay, so let's get into this monumental shift. For centuries, right, we had Isaac Newton. Gravity is this invisible force between objects with mass.
Yep, worked brilliantly. Explained planets, apples, everything we could see around us, pretty much.
But then Einstein, in 1915, he publishes his general theory of relativity, and it just turns everything on its head. How did he even get to the idea that gravity isn't a pull, but a bend in space and time itself?
It is a huge leap. And what's interesting, is that there were subtle hints even in classical physics. Think about objects just moving freely, no forces acting on them.
They go in straight lines, right?
Right, or what we perceive as straight lines. Einstein called these paths geodesics. But his big aha moment, it seems, came from thinking really hard about free fall.
Oh,
He came up with this amazing thought experiment, his famous elevator experiment. So imagine you're inside a closed room, like an elevator, floating in space maybe. If you drop a ball, well, how do you know if that elevator is just sitting still on Earth in its gravity field? Or what if it's actually way out in space, completely free of gravity, but accelerated upwards at exactly 9.8 meters per second squared, the same as Earth's gravity?
I see where you're going. From inside, the ball would fall to the floor in exactly the same way in both cases.
Precisely. There's no experiment you can do inside that box to tell the difference between being in a gravitational field and accelerating uniformly.
So you literally can't distinguish gravity from acceleration locally. That's quite something.
It really is. He called it the equivalence principle, this universality of free fall. It was the key insight. It suggested gravity wasn't a force like other forces.
Because you can usually tell if you're being pushed by a force, right?
Exactly. But free-falling objects, they all behave the same way, regardless of what they're made of. They seem to be following the most natural path possible through something. And that something, Einstein realized, must be space-time itself.
So gravity isn't something you feel pulling you. It's just the shape of the space and time you happen to be moving through.
That's the idea. The presence of mass and energy actually curves or warps space-time around it. And objects, even light, just follow these curves, these geodesics. Like a marble rolling on a dented rubber sheet, it follows the dip.
So the core idea then is that gravity isn't this invisible hand. It's literally a change in the geometry of space and time that tells things how to move. I love that quote by John Wheeler.
Oh yeah, space-time tells matter how to move. Matter tells space-time how to curve. It sums it up perfectly.
Beautiful.
And this isn't just a neat analogy, it's mathematically precise. Einstein's field equations, they're the heart of it. They're a set of equations that explicitly link the geometry of space-time, its curvature, directly to the amount of matter and energy present.
So the math actually describes how much space-time curves based on what's in it.
Exactly. They're complex, nonlinear equations, but they capture this dynamic relationship. Geometry dictates motion, matter creates geometry.
Okay, so this geometric view, it's elegant, but does it actually work?
Yeah.
Does it predict things differently than Newton? Things we can actually see?
Oh, absolutely. And that's where it gets really compelling. General relativity predicts phenomena that Newtonian gravity simply can't explain. These are the universe's own confirmations, showing space-time geometry is real and active.
Like what, for instance?
Well, first off, this warping affects time itself and light.
Wait, gravity actually messes with time. How does that even work? How could we test that?
We can, and we have, with incredible accuracy. It's called gravitational time dilation. Basically, time runs slower closer to a massive object where gravity is stronger.
Slower, like literally ticking slower.
Yes. Clocks closer to Earth's center run measurably slower than clocks higher up, say on a mountain or in an airplane. We've confirmed this with super precise atomic clocks.
Wow.
And it's not just theoretical, it's crucial for things like the GPS system. The satellites orbiting Earth are in a weaker gravitational field than we are down here.
So their clocks run faster.
Exactly. They run slightly faster. If engineers didn't constantly correct for this relativistic effect, both time dilation due to gravity and time effects due to their speed, your GPS directions would drift off by miles every single day.
That's amazing. So GR is part of our everyday tech.
It absolutely is. And this warping also affects light. When light climbs out of a gravity well, it loses energy. Its waves get stretched out, shifting towards the red end of the spectrum. We call that gravitational redshift.
And presumably the opposite happens if light falls in. It gets blue shifted.
Precisely. Gains energy, frequency increases. But maybe even more dramatically, gravity bends the path of light itself. Since light has to travel through space-time, if space-time is curved, light's path curves too.
Ah, and that's the famous test during the solar eclipse, right?
It's the one. Arthur Eddington's expedition in 1919. They observed starlight passing near the sun during a total eclipse and found it was deflected by just the amount Einstein's theory predicted. It was huge news. Made Einstein famous overnight.
So the sun's gravity literally bends starlight passing by it. Does this bending effect show up elsewhere?
Oh, yes. Big time. It leads to gravitational lensing. Imagine a really massive object, like a galaxy or a whole cluster of galaxies, sitting between us and a more distant light source, like another galaxy or a quasar.
Okay.
That intervening mass acts like a lens, bending the light from the distant object as it passes by. This can create multiple images of the background source or distort it into arcs, even complete circles called Einstein rings.
So we see multiple copies or weird shapes of distant things because of gravity bending the light.
Exactly. And astronomers now use this as a tool. It's like a natural telescope, allowing us to see galaxies that would otherwise be too faint. It also helps us map out where mass is, including invisible dark matter, because dark matter still exerts gravity and can act as a lens.
That's clever, using gravity itself to see things.
It is. There's also the Shapiro time delay. Basically, light takes slightly longer to travel through a gravitational field than it would through flat space. We've tested this by bouncing radar signals off planets like Venus and Mars when they're on the far side of the sun from us. The signals take a tiny bit longer to return, just as GR predicts.
Incredible precision. What else? You mentioned cosmic dances.
Right. Orbits aren't quite the perfect ellipses Newton described. They wobble, they precess. The point of closest approach in an orbit, the perihelion, actually shifts slightly with each orbit.
Okay.
For decades, Mercury's orbit had this tiny anomaly. Its perihelion shift was just a little bit faster than Newtonian gravity could account for. It was a real puzzle.
And Einstein's theory.
Nailed it. Perfectly. General Relativity explained Mercury's anomalous precession as a natural consequence of the way space-time is curved by the sun's mass. No exoplanets needed, no fudge factors. It was a major triumph for the theory.
So what was a nagging problem became strong evidence.
Exactly. But maybe the most spectacular prediction was gravitational waves. Actual ripples in the fabric of space-time itself, caused by accelerating massive objects like colliding black holes or neutron stars.
Ripples in space-time. What would that even look like?
Imagine space itself being squeezed in one direction while being stretched in the perpendicular direction, then oscillating. These ripples travel outwards at the speed of light.
And these were predicted way back then.
Yep, by Einstein. For decades, the evidence was indirect. Astronomers Hulse and Taylor discovered a binary pulsar, two neutron stars orbiting each other, and they measured its orbit decaying over time.
Meaning they were getting closer.
Yes, spiraling inward. And the rate at which they were losing orbital energy perfectly matched the rate predicted if they were radiating energy away as gravitational waves. That discovery earned them the Nobel Prize in 1993.
Wow. So we knew they had to exist based on that.
Pretty much, but the ultimate proof came much later. After decades of building incredibly sensitive detectors.
LIGO.
Exactly. In 2015, announced in 2016, the LIGO detectors made the first direct detection of gravitational waves. They picked up the signal from two black holes merging over 1 billion light years away.
That must have been an absolutely incredible moment for physics. A century after the prediction.
Monumental. Just monumental. It opened up a whole new way to observe the universe. And there are even more subtle effects, like geodetic precession, basically. The axis of a spinning gyroscope in orbit will slowly change its orientation relative to distant stars because of space-time curvature, tested by the Gravity Probe B satellite.
And frame dragging. That sounds cool.
It is. Rotating masses, like the Earth or a spinning black hole, actually drag space-time around with them, like stirring thick honey. It's a tiny effect for Earth, but measurable. Gravity Probe B confirmed this too. Near a spinning black hole, this effect is so strong it forces everything nearby to rotate along with it.
Okay, that's an amazing track record of predictions. But you mentioned black holes. What happens when space-time gets really bent out of shape, like the most extreme cases?
Right, that's where black holes come in. General relativity predicts that if you concentrate enough mass or energy into a small enough region, space-time can become so intensely curved that it essentially tears, forming a boundary called the event horizon.
And nothing can escape from inside that, not even light.
That's the definition. Once something crosses the event horizon, its future path inevitably leads towards the center, the singularity. Light can't get out, so they appear black.
Are these just theoretical curiosities or are they real?
Oh, they're very real. We have overwhelming evidence. They're thought to be the final stage in the life of very massive stars. And we also believe supermassive black holes, millions or even billions of times the mass of our sun, lurk at the centers of most large galaxies, including our own Milky Way.
And they're important for galaxies somehow, not just cosmic sinkholes.
Absolutely. As gas and dust fall towards a black hole, they form an accretion disk, getting incredibly hot and radiating huge amounts of energy across the electromagnetic spectrum. This process can power things like quasars and launch enormous jets of particles traveling near the speed of light. They play a big role in galaxy evolution.
Okay, so black holes are one extreme. What about the universe as a whole? How does GR fit into cosmology?
GR is the foundation of modern cosmology. Einstein's field equations, when applied to the universe on the largest scales, describe its overall dynamics and evolution.
The Big Bang and all that.
Exactly. The standard model of cosmology, based on GR, describes a universe that began in an incredibly hot, dense state about 14 billion years ago and has been expanding and cooling ever since.
And this model actually works. It explains what we see.
Remarkably well. It correctly predicts the abundances of light elements like hydrogen and helium created just minutes after the Big Bang. It predicted the existence of the cosmic microwave background radiation. The afterglow of the Big Bang and its properties match observations beautifully. It explains the large-scale structure of galaxies we see today.
But it's not perfect, right? You mentioned dark matter earlier.
Right. GR, combined with observations of how galaxies rotate and how light bends around galaxy clusters, tells us there's far more gravitational pull than we can account for with the visible matter, stars, gas, dust. About 85–90% of the matter seems to be this invisible dark matter. We know it's there because of its gravity, but we don't know what it is.
Another mystery.
And then there's dark energy. Observations of distant supernovae in the late 1990s showed the expansion of the universe isn't slowing down. As you might expect due to gravity, it's actually accelerating.
Accelerating. What's pushing it?
We don't know. We call the cause dark energy. It seems to be some kind of energy inherent in space itself, acting like a sort of anti-gravity on cosmic scales. Einstein actually had a term in his original equations, the cosmological constant, which could represent this. He later called it his biggest blunder, but, well, it seems he might have been right after all, though perhaps for the wrong reasons initially.
So GR points to these huge unknowns. Dark matter and dark energy make up like 95% of the universe's energy content, and we don't know what they are.
Precisely. It's both a triumph and a challenge. The framework works incredibly well, but it reveals these profound mysteries. And beyond that, there are even more exotic theoretical possibilities within GR, like solutions suggesting closed time-like curves, potential pathways for time travel, though likely physically impossible, or ideas like warp drives. These usually require things like negative mass or energy, which we have no idea how to create.
So fascinating theoretical ideas, but maybe not practical.
Not anytime soon, let's put it that way. They show the mathematical richness of the theory, but they often clash with other known physics or require impossible ingredients.
Okay, so GR has been incredibly successful, predicting everything from GPS corrections to black holes in the expanding universe. But you mentioned it points to mysteries, and it's not the final word, is it? What's the biggest challenge it faces now?
Yeah, despite all its power, GR isn't the complete picture. The single biggest challenge, the sort of holy grail of theoretical physics right now, is reconciling general relativity with quantum mechanics.
The two pillars of modern physics, right?
Right.
Gravity and the quantum world. Why don't they get along?
They describe reality in fundamentally different ways. GR describes gravity as the smooth, continuous curvature of space-time. It's deterministic. You tell me the starting conditions, I can tell you exactly what happens. Quantum mechanics, on the other hand, describes the other forces in particles at the smallest scales. It's inherently probabilistic, deals with discrete units, quanta, and involves concepts like uncertainty and superposition that just don't mesh well with the smooth geometry of GR.
So it's like trying to fit a square peg in a round hole when you get to really extreme situations.
Exactly. Situations where gravity is incredibly strong and confined to tiny spaces. Think about the very center of a black hole, the singularity, or the universe at the very instant of the Big Bang. You need both theories there, but they give contradictory answers. Infinities pop up. It tells us our understanding is incomplete.
Is there any progress in bridging this gap?
There is. Physicists have developed something called quantum field theory in curved spacetime. This is like a halfway house. You treat matter and energy using quantum rules, but you place them on a background spacetime that's still described by classical GR.
Does that lead to anything interesting?
It does. One of the most famous predictions from this approach is Hawking radiation. Stephen Hawking showed that quantum effects near the event horizon of a black hole should cause it to emit particles very slowly, as if it had a temperature. This means black holes aren't truly black, and they can actually evaporate over immense timescales.
Wow, so quantum effects make black holes glow, essentially.
In a manner of speaking, yes. It's a beautiful result connecting GR, quantum theory, and thermodynamics, but it's still not a full theory of quantum gravity because space-time itself isn't treated quantum mechanically.
So what would a full theory look like? What are people working on?
That's the big quest. A theory of quantum gravity. A theory where gravity itself emerges from quantum principles, where space-time might be quantized. There are several leading candidates, though none are experimentally verified yet.
Such as?
Well, probably the most famous is string theory. It proposes that the fundamental building blocks of reality aren't point particles, but tiny, vibrating one-dimensional strings. Different vibration modes correspond to different particles, including the graviton, the hypothetical quantum particle of gravity.
Strings, okay. Does it work?
It's mathematically very rich and potentially offers a unified framework for all forces and particles. But it also predicts extraspatial dimensions beyond the three we see, and it's been very difficult to make testable predictions.
What else is out there?
Another major approach is loop quantum gravity, LQG. It takes a different route, starting with the principles of GR and trying to quantize spacetime geometry directly. In LQG, space isn't smooth and continuous at the smallest scales. It's fundamentally granular, like a fabric woven from discrete loops or a network.
So space itself comes in tiny chunks, pixels of reality.
Kind of, yeah. It suggests area and volume have minimum possible values. LQG focuses specifically on quantizing gravity and doesn't necessarily aim to unify all forces like string theory does, at least not initially. Both approaches and others face huge challenges, both theoretical and experimental. We don't have experiments sensitive enough to probe the Planck scale, where these quantum gravity effects would become obvious.
So the search is definitely on, but we're not there yet.
Not yet. But it shows that even over 100 years after Einstein gave us general relativity, it's still pushing us forward, pointing towards deeper layers of reality we haven't fully grasped. It's an unfinished symphony, still inspiring new research.
It really is incredible how one idea continues to shape so much of physics. Thanks for listening to this deep dive. We'd love to hear your thoughts in the comments. How might this geometric view of gravity, this idea of curved spacetime, actually help us figure out dark matter and dark energy? Or could it even be the key to finally uniting gravity with the quantum world? Let us know what you think.
Yeah, great questions to ponder.
And please subscribe to the channel. It really helps more listeners find these discussions. Thank you. And have an amazing day.